Bismillahirrahmanirrahim. So the topic is MIMO. We're going to see the brief introduction of the MIMO for this part. We're studying this topic of MIMO because MIMO has a key role in uh, the massive MIMO beamforming in the 5G networks and the 6G networks. So in order to understand that, we need to know the basics of MIMO first. So these are actually the basics of MIMO, and we are thankful to University of Medicine, Wisconsin Medicine. We're using the slides of University of Wisconsin. Okay, so for MIMO, MIMO basically stands for multiple input, multiple output. We have transmitter and receiver that can have multiple antennas, right? A modern wireless communication technology. Right? The theory of that started in late 1980s, and the standards and products were made after 2000s. So now core feature in wireless LAN and cellular network is MIMO, especially for the 5G, we have massive MIMO, where we have thousands of antennas. But first, we obviously need to know the basics of MIMO. So what are the two key benefits of MIMO? The first one is the improved link signal to interference noise ratio. And the number two is improved link concurrency, that is simultaneous parallel uh, transmission and reception. So these are the two key advantages of a MIMO network. Okay, MIMO network architecture. The first one is the single user MIMO. Basically, it was used in 802.11n in year 2009 and also in the 4G LTE networks. We have one transmitter, one receiver. Either transmitter, receiver, or both can have multiple antennas. We have one transmitter and we have a one receiver. Either transmitter or receiver or both, they can have multiple antennas, as you can see over here. In case of multi-user MIMO, that was used in 802.11 AC 2014, and also in the advanced version of the 4G LTE advanced, we have one transmitter and multiple receivers. So parallel transmission can be done. So this transmitter can parallelly send data to this system, and this system simultaneously, right? So this is the multi-user MIMO. So that was a single user MIMO, whereas this is the multi-user MIMO. The next one would be the network MIMO that is expected in near future. Rather, this is already implemented in 5G systems, that we have network MIMO, where we have multiple transmitters and multiple receivers. Parallel transmissions are going on. So we have this transmitter, this transmitter, and multiple receivers and multiple transceiver transceiver system is operating in parallel. That is the network MIMO. Okay. Okay, so basic communication modes of single user MIMO. That is the SISO, that is CISO, the single input, single output. You have a single input and a single output, that is a CISO network. And then we have a single input, multiple outputs. The single input where we have multiple outputs on the receiver side, a SIMO. So this transmitter is transmitting to this antenna and this antenna at the same time. This is SIMO. And then we have MISO, where we have multiple antennas on the transmitter side and a single antenna on the receiver side. This is a MISO. And then we have MIMO, where we have multiple antennas on the transmitter side and multiple antennas on the receptor side. And we have multiple data streams. That, for example, this antenna is transmitting to this antenna of the receiver. This antenna of the transmitter is transmitting to the second antenna of the receiver. The second antenna of the transmitter is transmitting to the first antenna of the receiver. And the second antenna of the transmitter is also simultaneously transmitting to the second antenna of the receiver. So this is a MIMO network, right? Whereas we have a single user MIMO. For example, a single user have multiple transmitting antennas and multiple receiving antennas, right? Okay, what are the MIMO benefits? An audio metaphor is being created over here. You can see we have an ear, and this is a sort of a ring bell. In case of SIMO, we have 2 ears, right? But obviously, all of you know that whatever you hear, courtesy of both of your ears, you hear a single consolidated noise, voice, right? So this is what the nature, the Almighty Allah has gifted us. That the processing is so neat and clean, and both of these ears are listening to something, and single consolidated information is being fed to the brain, and we hear that. Okay, coming to MISO, we have two bells in the single ear, and 2 ears and two bells for the MIMO. So this is sort of an audio metaphor, a very interesting one. Single user MIMO benefits, we have capacity gains. The first one, the diversity gain. We have already studied this topic of diversity, and we know that what diversity is all about. We have receiver diversity, we have transmitter diversity, we have multiplexing gain, that is a spatial multiplexing, for example. For the receiver diversity, the receiver coherently combines the signal received by multiple antennas, right? So in case of SIMO, you can see over here, we have a transmitter and two antennas. The asymptotic gain, the increasing SNR proportional to the number of receiving antennas. The more the number of receiving antennas, the better SNR there would be. The intuition is the received signal power adds up, right? The received signal power gets added up, and hence more signal power divided by the noise power, and hence greater SNR. What's the capacity gain? For the capacity, we know that it's the Shannon equation, that is a C is equal to B, that is the bandwidth, log base 2, 1 plus SNR. This is, the infamous Shannon's equation. So when the SNR is low, this can be approximated to the capacity is directly proportional to the SNR. So gain is almost linear with respect to the number of antennas. This number of antennas is also related to this signal to noise ratio. So we can say that greater the number of receiving antennas, the linear sort of improvement in case of the capacity. Okay, implementing receiver diversity. We have discussed diversity combining techniques already. So you know that we can have sort of selection combining, where you select the best antenna. For example, you have NR number of antennas. So you go with the best antenna which has the greatest SNR, and you select that. In case of maximal ratio combining, you put weights and combine the effect of all the antennas and try to maximize the SNR. And it is courtesy of the weight that you get a consolidated better SNR. Mitigating failing with the receiver diversity. On the y-axis, we have SNR. On the x-axis, we have frequency bin. So in case of the blue line, this is for the antenna one. This is for the antenna one. And you can see that for certain frequencies, we have the notches. Notches are sort of the glitches, or, the sudden fall in the SNR for a certain frequency. That is the notch. For antenna 2, again, you can see that the behavior is a bit different. For example, we had the notch for this antenna 1, but for this frequency range, we have a good SNR, right? And then we have some, a glitch at sort of this frequency where we have better performance for the blue one. So if we combine the effect of both of these, that would be the best scenario, right? So antenna 1 combined with antenna 2, that would give us the best scenario. The multiple receive antennas allow compensation of by non-notches in others. So this is how you mitigate the effect of fading courtesy of the receiver diversity. That is more number of antennas. With regards to the transmitter diversity, the transmitter sends multiple versions of the same signal through the multiple antennas. Two modes of transmit diversity is there: open loop transmit diversity, and the other one is the closed loop transmit diversity. Okay, so what is the open loop transmit diversity? In the open loop transmit diversity, the principle is that you send redundant versions of the same signal over multiple time slots and through multiple antennas, right? So you're sending the redundant version of the same signal over multiple time slots through multiple antennas. So let me go to the next slide first. You can see that we have time slot 1 and the time slot 2. In the time slot 1, you're sending the symbol S1 and S2, and H1 and H2 corresponds to the channel. So the RT1, that is the received signal at time instant T1, would be H1 S1, H1 convolution with the S1, or the, in case of the frequency version, you can say the multiplication of these two, but that is how you write, plus H2 S2. And for the time slot 2, instead of transmitting symbol S1 and S2, we send minus S2 conjugate and S1 conjugate, right? So this technique is also known as space-time block code, where you encode the symbols differently for different time slots and transmit antennas in order to improve the performance, right? So this technique is known as space-time block code. You send S1 and S2 at time instant T1, and you send minus S2 conjugate and S1 conjugate at time instant T2. RT1 and R22 would look like something like this, right? Okay. So in case of diversity combining, you will combine the effect of RT1 and RT2. So that would be H1 conjugate RT1 plus H2 RT2. And by that, you will have H1 square plus H2 square. So the signal power is boosted from H1 square, H1 square plus H2 square. So obviously the signal power is boosted. The open loop transmit diversity gain, in general, open loop transmit diversity increases SNR linearly with the number of transmitted. So it is linear increase. So that is a linear increase where we had H1 square for the power, and now we have H1 square plus H2 square. The next one is the closed loop transmit diversity. The basic principle is that you send redundant versions of the same signal over the same time slot. In case of open loop transmit diversity, we had two different time slots. Here we are sending, in case of closed loop transmit diversity, we are sending the redundant version of the same signal over the same time slot. You encode the symbol differently for different transmit antennas. That is, you weight the symbols of 10 different antennas following a pre-coding algorithm. The pre-coding design requires feedback of channel state information. Okay, let me come back to this. But before that, let me move on to this point, that you're sending the data over the same time slot. So you don't have T1 and T2. You only have RT1 in that case. You don't have RT1 or RT2, because you're sending the symbols on the same time slots. But again, you're encoding the symbol differently for different transmit antenna, like the one we had done already for the space-time block code. You weight the symbols on different antennas following a pre-coding algorithm. The pre-coding designs require the channel state information. So I'll talk about that. You can see that we have a transmit diversity encoder. We have multiple antennas, a single receiver over here. The receiver is also feeding back its information, or a feedback channel is there, and it is coming back to the transmit diversity encoder. So why is that? Why there is a need of a pre-coding? So since the signals from different antennas need to sync align their phases, but the different channels between the transmit antennas and receiver antenna distort signals differently, causing phase offset. Both transmit antennas send X is equal to EJ 2 pi ft. For example, this is sending EJ by 2 ft. This is also sending EJ 2 pi ft. But receiver may receive EJ 2 pi ft on one antenna, but EJ pi 2 ft plus a phase offset of pi from the other, which weaken the other signal. So it is weakening the overall effect. For example, we have only one antenna on the receiver side. So the both of these signals are nullifying the effect of each other, and hence weakening the signal. So pre-coding is important. So what does pre-coding help? Transmitter compensates the phase offset and aligns the phases of signals going through different channels. So instead of sending a signal X from antenna 1 and X from antenna 2, it will send X from antenna 1 and X E minus J pi from antenna 2, so that there is no overlapping of the constructive and destructive interference, hence nullifying the effect of each other. Rather, it will boost the effect of each other. So for that, we should have, the feedback channel information. We need to know what the phase offset is. So if we come up with this information, what the phase offset is, only then we will be able to transmit in a way so that the nullifying effect is no more there. And therefore, we need to have this channel state information feedback. And this is known as the pre-coding. So transmitter must know the phase offset in order to perform the phase compensation. The asymptotic gain from closed loop transmit diversity, the signal level combining, also called the transmit beam forming. Suppose we have two transmit antennas, then instead of X, we receive X plus X, that is the 2X. The seed power becomes 4X square. So SNR is increased to 4 times. So in case of closed loop diversity, we had an increase, a linear increase, whereas here we have a significantly more sort of, you can say, close to the exponential sort of an increase. More generally with anti-transmit antennas, the SNR increases to, NT square. So that is why closed loop transmit diversity is, in terms of this, is it's much better. But obviously, you need to have the channel state information, and hence you need to perform this pre-coding procedure. That was a very simple and naive introduction of MIMO. We will talk about MIMO in more detail, inshallah, in the next lecture. For meanwhile, I'm going to end this topic of the basic introduction of